In the first video of this series, entitled All of the Ebow Schematics You've Seen Are Wrong, I discovered that all of the Ebow schematics on the internet are wrong, and I theorized about how the circuit may work. The second video was to correct a few errors that I made in the first one. In Ebow Resurrection Attempt Part 1, I reassembled a completely destroyed unit that I obtained from someone after their unfruitful attempt at uncovering its secrets. I had to rewind both the driver and input coils, guessing at what the actual target was. In Ebow Resurrection Part 2, I created a testing jig, tried different spice simulations of the circuit, and ended up with a unit that didn't work. I thought that was the end of the road, but because I felt like the goal was still in reach, I decided to revisit the project. In this episode, Part 3, I finally conquered this fascinating, simple yet complex beast. This will not be a short video, and I condensed it as much as possible, but I hope that you will find it interesting nonetheless. We will go through the whole testing and research process, and at the end, we will see how close the spice model is to the real world. And I will summarize how this circuit actually works. Here's an interesting little test. I've got the Ebow on. My finger's muting the string. I'm going to just slide my finger back onto the bridge here. It's going to start oscillating all by itself. Now with it not plugged in to an amp or anything, it just sounds like an oscillator pretty much, like something I'd use to test circuits when I'm done with them, see if they pass a signal, right? So then I thought, that's interesting. Wonder if we could figure out what frequency that is. So I got out the function generator with a sine wave and run it into an audio amp. Listen to that. It's oscillating around 750 hertz. I can't get this function generator to totally nail an exact frequency, but sounds like it's right around 750 hertz. Interesting, huh? The Ebow test fixture has morphed once again. I've added a couple of things to it. One is I made a bracket to securely hold this potentiometer that's wired in place of the feedback resistor. Makes it easier to measure stuff. I added a switch here, reversing switch, which will reverse the direction of the diode so I can demonstrate what happens when you reverse the diode. I added a pair of wires that come off the capacitor on the input, so I can add a capacitor in parallel to mess with the frequency of the oscillator. The other thing I did was I put the original 4.7 microfarad cap back in the circuit, because I think that this bit me in the butt that it actually does matter, because it kind of forms a filter of sorts, and the 10 UF I think is too big, so I put this one back in. It actually tests okay. So back in the circuit it went. The other thing I did is I rewound the output coil. The original winding, I think, should have actually measured way more than 8 ohms, because it was small wire and I had even more than what's on here now. And I don't know, maybe there was a short or something was going on with that. It just wasn't right. So what I did is I took apart another transformer that I pulled out of some piece of equipment many years ago. Maybe it was a dead fax machine or something like that. But it has considerably thicker wire than anything I've used on here yet, and I think it's 22 AWG. And so I rewound the input coil, and at first I was winding it, and I wound it to 8 ohms, and it just seemed like barely any wire on the thing. And I thought, that can't be right. There's not enough wire on there. So I thought, well, okay, I've seen on the data sheet, you know, they show 8, 16 ohms. You can wire it up for a headphone, this would be 32, and so I wound it to 16 and it still seemed like hardly any wire on there, and I thought, it occurred to me, well, maybe there's like a 10-to-1 ratio thing going on with this. Maybe the output coil is like 1/10 of the input coil. Just for kicks, I was like, okay, I'll try it. So, um, but that was after I wound it to 32 ohms. So I wound it to 32 ohms, put it in the circuit, and it was a big improvement. I could get the string to vibrate pretty vigorously. But the thing was that it still wasn't strong enough compared to the actual Ebow that's functioning properly. So I took it off and I added some more wire to the one end here and wound it up to 46 ohms, put it back in. That was a really big improvement. Honestly, I'm not sure that's enough still, but we'll see when I do my string vibration test that you know, this thing's going to really get the string going pretty good. So the couple of problems I'm having now, and you know, I may not ever be able to get this back to exactly the way it was before it was torn apart, but I consider it a success that I can actually get it to vibrate the string and get it to function on some level. So but anyways, when we do the string vibration test, we'll see that one of my problems is the harmonic mode doesn't really work. Okay, and so the other thing is when I switch between modes, I have to monkey around with the resistance of the feedback resistor to get it to vibrate the string. So obviously something's not optimized. There must be some kind of special relationship between the amount of windings on both coils and obviously the direction of the magnets, you know, North Pole, South Pole, etc. I'm almost wondering if these are kind of set up in a sort of humbucking or noise canceling setup where the noise from one coil is supposed to cancel out the other, and I don't have it functioning for some reason. I don't know. The other thing I did is I did a compass test, which someone had suggested I try. And on the Ebow, the factory Ebow that's not been destroyed, you can see that the north basically is pointing inwards on both, just about on both magnets, right? So this is driver coil, it's pointing inwards, input coil, it's pointing inwards. So the north poles are pointing towards each other. And so I've measured both of mine this morning, and so obviously I just showed you the factory Ebow, they point in towards each other. On mine I have the driver coils pointing north towards the center. The input coil is kind of off doing its own thing. So what I did is I added a small rare earth magnet here on the side, which I'm doing to try to mess with the North Pole just a little bit to maybe see if I can theoretically correct it slightly to help improve the performance of the circuit. So I guess the next thing to do would be to do the actual string vibration test, and we can show you some of the things I'm talking about. Yeah, and I failed to mention that the other thing is I cannot get this into a setting where it's not injecting noise directly into the pickup, and where both modes work, and also have it cause a string to vibrate. So these three things are not all coming together, but I still consider it a success that I've been able to actually get it to function on some level and get the string to vigorously vibrate. So we'll do that demonstration now. This strange looking contraption here is a one string jig that I created to make testing the Ebow a heck of a lot easier. The trying to test that Frankenstein with the testing jig and everything and on an electric guitar is just too impractical and a real pain in the butt to try to adjust things. And so I literally made this with just things lying around. For example, I had this one extra guitar tuner that I had lying around left over from a project I did some years ago, and it's attached to a piece of scrap aluminum. I have this spacer in here because it's not the it attaches something that's the thickness of a headstock, and attach this little thing here. It's a cable holder. Keep the wires off the capacitor substitution box out of the way. Add a little handle to make it easier to move around. This is a humbucker that I've had lying around the drawer for many years. That is what will pick up the signal from the string and send it to this output jack that I've wired some little solder lugs to make attaching the scope probe a heck of a lot easier. And then over here I had to create this kind of contraption to make the string the same height as where the tuner is. And it kind of reminds me of the offset sights on a Bren gun. But anyways, it's tuned. It's a B string, so it's basically tuned to an open B, which seems to be very responsive to the Ebow. It's one reason why I picked the B string. And the scale length, for anyone curious, it's 25.5 inches, which is the scale that all real electric guitars use. So here we're getting 80 millivolts on the output at the guitar pickup. So you can see I have to help it. The frequency of the oscillator has to be the same as the string for it to start to vibrate the string, but it is doing it all by itself. But it's still not strong enough for me to stick a screwdriver on here and have it change the pitch as if I was playing slide. I still have to manipulate the feedback resistor value to get it to latch on, but here you can see it's doing over 100 millivolts. It was. I'm having trouble getting it to latch on to something that's not the open B string here. There we go. Now here's what happens when you reverse the diode. It just kills the power. So we know that the diode can only go in one way. Now with the way mine is rebuilt, it seems to work best with like 0.033 microfarad in parallel with the 0.033 on the board, or with the 0.047, which I currently have it on here. So I'm thinking probably the output coil still doesn't have enough windings on it. I think I might have to go for like 100 ohms on it. I simulated it in LT Spice with some better models, and the program would suggest that with 100 ohms on it, this thing should sustain very well. So we're making progress, at least. The harmonic mode seems to be trying to do something. And then sometimes it wants to go into this 1 kilohertz oscillation, which I don't understand why it does that. So as you can see, I have to help it, the oscillation or the string, to get going by setting the frequency of the oscillator to the same frequency as the vibrating string, but still progress. Here's the other thing. See here, if I put it next to the pickup, it picks up the noise, right? So that could just be that it's not running at the right frequency. I think there's going to be a combination of things that happen for it to not make noise. So you're not injecting noise right into the pickup from the oscillator. But all right, we managed to get 80 or 79 ohms of wire on this little output coil. So time to put that back in the circuit and see how it acts. Hopefully, if what I'm thinking is correct, this thing should be functioning even better. So here's the secret of the Ebow, one of the secrets. It's the oscillation frequency for one. It allows you to cause a string to vibrate by placing it, I guess, the string into the magnetic field. And these coils are just kind of on the verge of doing something, but not quite. And the frequency that it's running at allows it to not be operating until you put the string in here, because otherwise you would have noise being injected into your pickup. So I'm going to demonstrate how that works. So it's not oscillating at all right now. We're going to start it up. So now we jumped all the way up to 1.78 kilohertz. It's going to go all the way up to about 2.12 and it cuts off, right? Okay, so at that point, now if you put this underneath the string, it'll start vibrating all by itself. And it now has enough oomph to it to where you can do the screwdriver test. Let's try that again. This has to be exactly in a certain spot on the string for it to work properly, and my input coil is a little cocked to one side, so it's not quite perfect. But so I'm going to demonstrate. It's going to go through the whole frequency range and not cut out like it was doing earlier. So that's basically what it's doing. It's not full-time oscillating like I initially thought. Now, of course, the harmonic mode's not going to work correctly. I thought it was not working correctly because I wasn't getting 3 times the fundamental, but I discovered that because I have it here and not over the pickup like you would normally be using the Ebow like this, you don't get the same effect. But when I put this over the pickup like it would be in the Ebow, then it works exactly the same pretty much. So if you place this Ebow over the pickup, like right over the pickup like this, I was seeing like 500-600 millivolts on the scope, and I was getting about the same amount of voltage out of this when it's placed over the pickup the way it normally would be. So it appears that this thing is fully functional now. So the feedback resistance ends up being somewhere around 177K. So in the original Ebow, or in the Ebow, on that circuit board, the one here that had the broken resistor, and I couldn't determine what it was. I thought it was 13K. It's actually appears to be 130K. So I'm not that far off. Of course, it's going to be different because mine's going to be different here than the factory one, because I had to rewind the coils, and I'm guessing what they should be, and I don't have the exact same wire gauge and so on. But basically it's functioning 100% now. So what I'm going to do next is I have to devise a way to flip this string jig over so it's upside down, so I can place it over the test fixture here so that it's oriented the way it would be when you're playing, when you're using the Ebow, and then you'll see that it basically sounds exactly like, it works the same way as an unmolested, non-destroyed Ebow. So I've found a way to flip my one-string jig upside down, and so I'm just going to demonstrate it working like it's supposed to. So that's the regular mode. Now you notice it sounds a little higher in pitch. That's normal. That's exactly what it does. I think it basically doubles the fundamental and triples it in harmonic mode. So in harmonic mode, it has a little trouble getting going, but there we go. So now we're triple the fundamental in the harmonic mode. And both of these are putting out about 1.5 volts peak to peak. It's hard to do this. I gotta hold it exactly just perfect. Okay. Regular mode works very well. Harmonic mode is still finicky. It has to kind of be coaxed into working, but so maybe that's what the diode is for in the circuit. Maybe it helps the harmonic, or the harmonic mode to actually get going. Since I had it working so beautifully on my test jig, I figured, what the heck, maybe I should just try to actually go from original goal and make it a fully functioning unit again. So I put it in the bottom piece, and Added a socket for the capacitor, and I glued on a 20-turn 500K pot here on the back so I could tweak the oscillation frequency, and I finally got it going. The unfortunate thing is it only has like 40% of the power it needs to excite the string and get it going, so other than that it works exactly the same as a untampered Ebow out of the factory. So I'll go ahead and demonstrate that for you here next. So you can see the output on this guy is just too low to be usable, but it's functioning the same way. Unfortunately, I don't know why, this is only putting out maybe 40% of what the untampered Ebow is putting out. But it functions the same way. And that's just to prove a point. I think probably the main problem is that the input coil needs probably something in the neighborhood of 150 more ohms of windings on the coil, and I can't achieve that with the tiny wire I have that was hard enough to wind just to get it to this point. So I still consider it a success though, because I mean I got 90% of the way there. See, it works the same way, it's just the output is too low. It's too low to be able to fret a string or do like a slide guitar. It just kills the oscillation. So that extra volt or 1.2 volts is all the difference between it working really great and not working at all. So you can see this one almost perfectly doubles the fundamental. The other one was just slightly higher. Functionally the same though, so I'll consider this resurrection a success. Let's take a quick look at the waveform at the input of the LM386 and at the output cap. So this is looking at the input. The input of the output cap. Let's change that setting there. Massively clipped sine wave. Output of the output cap looks like that. I'll switch it over to harmonic mode. The input of the LM386 looks like this. And then we'll look at the output cap. So this is the input of the output cap. Whoa. That's more like it. Input of the output cap. Output of the output cap. And once again, we're looking at the output of the output cap in the regular mode. There we go. And here is a look at the output of the output coil. That's regular mode. And harmonic mode. Voltage peak to peak is 8.9 volts. It's higher than I thought it would be. Back to the regular mode. Let's see what that peak to peak voltage is. .19. So we just saw waveforms in the real world, and now we're going to see how LT-Spice compares. This circuit is the way mine is currently, and we're just going to see how it models. So right now we're in regular mode, and so of course ideally we have a nice sine wave coming into the circuit. We know that's not going to be the case. It's going to come through the input coil, and according to LT-Spice, we're adding in, looks like that would be our oscillation frequency on top of our waveform. Yes. Okay, so And then we come out of the LM386 and we get some weird looking waveform that's not right. Now even with this model and the much improved model, it's still not doing what it's supposed to be doing, because the output of the LM386 is supposed to bias automatically to half of the voltage supply, and that's not happening here. I mean, we're only seeing not even barely 1 volt voltage swing here, right? And then of course we look at the output of the output coil, and that's what that looks like. Nothing like what we saw in the scope. So then we'll go into harmonic mode real quick and run it, and we can do a little comparison. So once again, we come in to the input coil. So it looks like going into the LM386. So we kind of have our original signal riding on top of the oscillator frequency, if you will. And then it comes out of the LM386. Once again, this weird clipped sine wave, which maybe if this program was actually simulating this doing a full 4.5 volt voltage swing, these things would grow and it wouldn't look so weird. So ignoring all that, this is what LT Spice says the output of the output coil is going to look like. And we didn't see anything really that looked like that in the real world. Now here's one other interesting thing you can do with LT Spice, which may be a little closer to real world results. This here is a simplified Ebow schematic, and we're modeling force and velocity and voltage. So the input, this is set up so that the input coil current is determining the magnetic field. The output coil magnetic field determines the force on the string. The voltage on the string model represents the velocity of the string, and the received coil voltage responds to the string velocity. So you can kind of see the effect of the feedback resistor here, just as an example. So we're going to look at the input of the LM386. And you can see there's the initial attack when you pluck the string, and then you get this kind of disturbance, and then it kind of goes back to what it was doing. And you can see you have tiny voltage here, you know, what, 500 microamps. So now if you come over here, change this to 130K and run it. Oh, and I failed to mention in the last one, you can see the response time is really slow. In this case, with the 130K feedback resistor, you know, less than 0.1 of a second, and the circuit is responding and making that signal bloom into a much bigger signal and then maintaining it. With the 13K resistor, we just don't get that. You can see the response time is very slow. It's more than half a second. And which brings up a point that I wanted to mention. It appears to me that this, through my testing, it appears to me that this is a 130K resistor. And I believe that because this is probably a 5-band resistor code, color code here. And it was probably brown, orange, black, orange, and that might be silver at the end. So apparently what's happened is that resistor broke right where the black band is. So it was very hard to try to determine what it is. And of course, they couldn't measure it because it was broken in half. So I think that clears up the mystery of the 130K resistor. Here's what we now know about the Ebow circuit. The circuit is an LC oscillator. The values of the input coil, input capacitor, and the feedback resistor determine the frequency at which it operates.
While we have not been able to determine the exact characteristics of the driver and input coils, we have some rough idea of what they probably are or need to be. The circuit is normally in a standby state. When a metal object is placed between the input and the driver coils, the oscillator begins to run through inductive coupling, and the frequency of the guitar string quickly takes over. Once the feedback loop is going, all it has to do is maintain it. Where you place the Ebow in relation to the guitar pickup determines how intense it is. The pickup output voltage can thus dramatically change. The circuit will self-oscillate at a frequency of approximately 2.4 kHz in the normal mode and 2.6 kHz in the harmonic mode. This is probably the optimal range for the circuit to excite a guitar string into vigorously vibrating in the range of frequencies possible on the guitar. The feedback loop, as the patent states, provides positive feedback. This is what enables it to cause a string, which is in a resting state, to begin vibrating very vigorously all on its own. The circuit takes advantage of a certain characteristic of the LM386. The output is always half the supply voltage. This enables a very stable positive feedback loop. The circuit needs to be capable of driving a guitar pickup output to around 1.5 to 2 volts in order for it to maintain enough strength for fretting notes. Too low of an output and the circuit can't put enough energy into the strings to keep the cycle going, as well as upsetting the oscillator. The polarity of the magnets appears to be both north poles facing each other. The exact composition of the magnets is not known, but they do appear to have a Gauss strength of somewhere between 1 and 3. The rings around the windings appear to be steel with some sort of coating on them. They are probably used as shielding and to help direct the energy towards the strings. The purpose of those two round pads under the output capacitor is still undetermined. And last, the circuit board is completely encased in some sort of hard goop. Some people think it might be a 2-part urethane. It smells a bit like gasoline when you pick at it. While it may be easy to come to the conclusion that it's done to prevent people from reverse engineering the Ebow, I believe it serves at least 2 other purposes: circuit stability and the prevention of microphonics. In my testing, I found that it's quite easy to go from a working circuit to one that wasn't. Once verified that the circuit is functioning properly, completely potting it in a substance which entombs the circuit board and which makes it like a brick makes sense from a reliability standpoint.